Hello, welcome to Module 17 of the online course on pericyclic reactions and organic photochemistry. We will continue with sigmatropic rearrangement and consider 1,5 hydrogen and 1,5 carbon migrations as well as cope rearrangement, which is a 3,3 sigmatropic rearrangement in this particular module. In the last module, we considered the 1,3 shift. A similar analogy is drawn here to illustrate the 1,5 shift in the case of sigmatropic rearrangement. If you consider the thick bond, which is a carbon R1 bond, for example, the R group is migrating to this particular position, so it is corresponding to a 1,5 carbon shift if the R group is a carbon. If R group is a hydrogen, it would correspond to a 1,5 hydrogen shift. Let us recall the Woodward-Hoffmann rule for the 1,5 carbon and hydrogen shift. Under thermal condition, suprafacial migration is symmetry allowed as well as geometry allowed. Photochemical migration is allowed only if the antifacial migration is possible in the case of the 1,5 sigmatropic rearrangement under photochemical condition. So the thermal 1,5 sigmatropic rearrangements are quite common. There are several examples that are known here. Now let us take for example this example where the migration of hydrogen is illustrated by this example. These two structures are essentially conformational isomers because of the carbon-carbon bond rotation that is taking place. This will be in rapid equilibrium with respect to each other. So in other words, they are conformers with respect to each other. In each of the conformer, the hydrogen migration is what is illustrated in this reaction. So at 250 degrees, the hydrogen migration takes place in this skin. When the hydrogen migration takes place in a suprafacial manner with respect to the pi framework, this is a stereochemistry of the resulting chiral center that is generated, and this is a stereochemistry of the double bond that is generated. You can see here when the hydrogen migrates, it is suprafacial with respect to the pi framework, and it attaches itself from the bottom face from here, resulting in the attachment of the carbon hydrogen bond at the bottom, and with the concomitant change in the hybridization of this particular carbon to an sp3 carbon as shown here. From this conformer, if the hydrogen is migrating, it is going to migrate from the top phase, indicating that the hydrogen ends up in the top phase with the resultant stereochemistry of this chiral center to be like this, and the resulting stereochemistry of the carbon-carbon double bond that is formed here to be like this. These two isomers are diastereoisomers. The reaction is highly stereospecific in the sense that hydrogen migration is suprafacial in both cases, resulting in the formation of either this a mixture of these two products, where the stereochemistry here is defined as this, with the stereochemistry of the double bond to be here. In other words, the stereochemistry of the double bond with this stereochemical double bond and with this stereochemical sp3 carbon is not formed in any of this reaction. There is no significant dependence of the rate on solvent polarity, indicating that you can rule out the possibility of ionic intermediates being formed during the course of the reaction. This solvent effect is consistent with a concerted hydrogen migration involving no reactive intermediates in this particular instance. Significant primary kinetic isotope effect is observed because during the course of the transition state, the carbon-hydrogen bond or the carbon-deuterium bond, as the case may be, depending upon the deuterium substitution in this particular molecule, a significant Kh by Kd, which is the primary kinetic isotope effect of about 12.2 is observed, indicating that the rate determining step, which is the single step reaction involving the carbon-hydrogen bond breaking, is significant in this particular case. Now 1,5 migration is preferred over 1,5 carbon migration. Why is that? In other words, it is possible to migrate the methyl group or the ethyl group instead of hydrogen. Now typically a carbon-carbon bond breaking is more difficult than a carbon-hydrogen bond breaking. It is of a lower energy pathway, so only the hydrogen migration takes place. Why is it that 1,5 hydrogen migration takes place over 1,3 hydrogen migration? Remember, 1,3 hydrogen migration, although it is possible in this particular case, it has to take place in an antifacial manner. Such an antifacial shift is, although symmetry allowed, it is geometry forbidden, and that is why this reaction does not take place. So the fact that the carbon-hydrogen bond is of lesser energy than carbon-carbon bond explains why hydrogen migration takes place in preference to the carbon migration. The fact that 1,5 migration is a suprafacial migration and 1,3 migration is an antifacial migration, which is geometry forbidden, will explain this particular question. Now the preference of 1,3 shift over 1,5 shift over 1,3 shift is illustrated by this example. Initially the 3,4 dideutyl substituted derivative was taken, and this particular derivative was made to undergo thermolysis. In doing so, if the reaction were to be a 1,5 shift, the deuterium in the 3 position will migrate to 7 position. The deuterium in the 4 position will migrate to 8 position, which would correspond to 1,5 migration. If you consider this to be 1 and 1, then it will be 2, 3, 4, 5. The 7 position will be the 5th carbon from the deuterium point of attachment. So 1,5 migration will result in the 7 position or 8 position. In fact, the 1,5 migration results in the formation of the 7 and 8 position deuterium substituted derivative. In other words, during the course of the migration, the deuterium scrambles only to position 3, 4, which is starting point, and 8, 7, and none of the 2, 5, 1, 2, 5, 6 positions are never occupied by the deuterium. So the deuterium scrambling is very specific, which is controlled by a 1,5 shift. If the reaction were to proceed through a 1,3 shift, this deuterium will end up in the 1 position here, and this deuterium will end up in the 6 position here. Such rearrangements are not taking place. So this fact that the deuterium label is specifically located only in 3, 4, 7, 8 position and not in 1, 2, 5, 6 position clearly explains that this reaction proceeds through a 1,5 hydrogen shift rather than a 1,3 hydrogen shift, deuterium shift in this particular case. The thermal isomerization of monosubstituted cyclopentane is very common. You can see here the example that is shown here. This is a monosubstituted cyclopentadiene derivative. This carbon-hydrogen bond is undergoing the migration to this specific position. So in the process of migration, another isomer of the cyclopentadiene is produced, and further migration will produce another isomer of the cyclopentadiene. The consequence of this migration is that you have a mixture of cyclopentadienes during the course of the migration that is produced. So if one were to do the thermal Diels-Alder reaction with the monosubstituted cyclopentadiene, one has to be very careful not to make this reaction take place simultaneously during the course of the Diels-Alder reaction, because if this reaction takes place, each one of them will be a Diels-Alder diene, resulting in an awful mixture of cyclooctets being formed from each one of these diene during the course of the Diels-Alder reaction. So Diels-Alder reaction with monosubstituted cyclopentadiene are typically carried out at low temperature. If the reaction doesn't proceed at low temperature, then catalysis using Lewis acid is a way to go with respect to carrying out the reaction at a low temperature. Now here is a thermal isomerization of 7,7-dimethyl cycloheptatriene. This is the starting point where you can see the methyl group is at this particular position and the gem dimethyl group is in this position. When the molecule is heated to 300 degrees, the methyl group seems to be migrating in terms of the relative position between the gem dimethyl group carbon, and the methyl substituted carbon seems to be changing with respect to each other. Here it is 2 carbons away, here it is 1 carbon away. This is adjacent carbon with respect to the gem dimethyl group and the methyl substituted carbon derivative. How does this reaction take place? Imagine a ring closing reaction involving this cycloheptatriene going to norcarene structure. This is essentially a electrocyclic ring closing reaction is what is taking place, and this is a electrocyclic ring closing reaction in a disrotatory manner will essentially produce this particular compound. Once this compound is formed, this is a cyclopropyl vinyl cyclopropyl derivative. This can undergo 1,5 carbon shift, for example. This carbon-carbon bond can be broken and it can be shifted over here, which would correspond to a 1,5 shift going through this butadiene unit here. And such a process, for example, this carbon-carbon bond is what is broken here. It migrates to this particular position. So this will be 1 and 1. 1, 2, 3, 4, 5. So attachment at this position. This is essentially a 1-2 shift, but we call it as a 1-5 shift because of the sigmatropic notation essentially tells you that it is a 1-5 shift. After the migration of this particular, this carbon-carbon bond can be broken and it can be migrated. Once the migrated carbon-carbon structures are there, they can undergo electrocyclic ring opening reaction in a reversible manner to produce, that would explain the formation of these two products from the starting material, which is this particular starting material. Mechanistically, it is illustrated here. The red bond is the one that is undergoing the breaking, and that results in the formation of the new red bond between this carbon and this carbon, which corresponds to a 1,5 shift with the concomitant migration of the pi electrons. Now the carbon-carbon black bond is migrating, That would result in the formation of this particular product, resulting in the ring opening product to give the isomerized products of 7,7-dimethyl cycloheptatriene in this case. So there is a series of walk around the ring rearrangement that is taking place in this particular 1,5 sigmatropic shift, followed by electrocyclic ring opening reaction to explain the formation of these products in this particular case. In the case of 7,7-dicyanonorcaradiene, it remains in the norcaradiene form and does not remain in the cycloheptatriene form, for example. So the thermal isomerization takes place at a lower temperature in terms of the isomerization of the walking of the gem dicyanomethyl group. For example, this particular carbon bearing the gem dicyano groups, for example, essentially walks around the ring in this manner to give this particular product. So the thermal isomerization reaction of this type is what is known as the walk around the ring rearrangement, because this carbon is essentially walking over the ring, forming the various intermediates that are shown in this particular example. The walk around the rearrangement process can be cartoonically represented by this particular picture. Imagine that there is a shaded substituent, which is this particular substituent, and an unshaded substituent, which is this particular substituent. With respect to the butadiene unit, this shaded substituent is endo and the unshaded substituent is exo with respect to the pi framework here. What is happening in the case of A during the course of the walk around rearrangement, if you look at the molecule from the top position, in other words from the top of this pi planar 5 framework, you would see this carbon which is masked in this particular position, and the shaded and the unshaded carbon, which is the shaded carbon inside, let us say for example this would be the carbon, the unshaded carbon outside, which is this particular carbon. So essentially a view perpendicular from above the cyclohexadiene ring will show the molecule in this particular position. In the case of the suprafacial migration, the inside and the outside group will be alternating with respect to each other during the course of the migration. For example, a 1,5 sigmatropic migration to bring this carbon over here would end up taking this shaded portion outside and the unshaded substituent inside if it were to be a suprafacial migration. If it is an anterofacial migration, what remains inside will always remain inside. What remains outside exo will always remain exo with respect to the pi framework. So here is a situation. The structure A would correspond to a superficial migration where the shaded and the unshaded substituents alternate the exo and endo position during the alternate migration. Whereas if it is an anterofacial type of a migration, the exo substituent remains exo throughout the migration and the endo substituent remains as endo throughout the migration. Why does this take place like this? This is explained using the simple mechanistic scheme here. Consider a superficial migration of this particular carbon. Hydrogen A is endo, hydrogen B is exo with respect to the pi framework in this case. If there is a superficial migration that is taking place, that means this bond has to break. This carbon-carbon bond has to break, and once the bond is broken, this is a lobe that is going to interact with both the carbons in a simultaneous manner because it is a concerted process. So in doing so, it will bring the HB inside and HA outside, resulting in the formation of HB to be now the endo substituent and HA to be the exo substituent. So what was originally endo has become now exo. What was originally exo has become endo as a result of a suprafacial with the retention of stereochemistry resulting here. If it were to be an anterofacial migration, then the bond is broken here and the backside lobe is now going to attach itself to this particular position. So as a result of that, inversion takes place, but then the endo substituent remains as endo, the exo substituent remains as exo. So in a walk around rearrangement, if it is happening in a suprafacial manner, the exo endo substituent will alternate during the course of the rearrangement between the exo and the endo position. If it is an anterofacial migration of the rearrangement, then what was remaining as the exo substituent will remain exo throughout the migration. What was originally an endo substituent will remain as an endo substituent throughout the migration, which is explained by this mechanism of retention and inversion of stereochemistry. In one case, the suprafacial migration is taking place. The other way, anterofacial migration is taking place with respect to the sigma bond that is being broken in the course of rearrangement. Here is a rare example of a migration of a nitro group in a 1,5 position, 1,5 shift. This is a ipsonitration product. The ipsonitration product has the nitro group attached to this particular carbon. Remember, the stereochemistry of the nitro is actually the inside is the nitro, and the what is projecting in front of us is the methyl group. And during the course of the rearrangement, the nitro remains superficial migration with respect to the pi framework, so it remains interior, and the hydrogen which was originally here now is pointing towards us, for example. So this is a regio-specific as well as a stereo-specific reaction. It's a regio-specific because it's a 1,5 nitro shift. It is a superficial migration, and that is why the stereo-specificity also gets into picture. The reaction is clearly superficial with respect to the NO2 migration, is what is illustrated in the example. Now let us consider the photochemical 1,5 hydrogen migration in an antifacial manner. In these reactions, the two pi systems are not planar with respect to each other. Because of the steric hindrance between these two methyl group, this pi will be pointing up, or this pi will be pointing down, or vice versa, as the case may be. That brings the hydrogen to be in a favorable position for the antifacial shift. Remember, it is a photochemical reaction. 1,5 migration should be antifacial. So the migration of this particular hydrogen over here results in the formation of this particular compound. And the steric effect essentially, which leads to the non-planarity of the pi bond, is what is responsible for the facile antifacial migration in both cases. These are two examples of antifacial hydrogen migration. One can also have a antifacial hydrogen migration. There is a double bond missing here. I am sorry. There should be a double bond here. The hydrogen is migrating to this particular position in an antifacial manner, resulting in the formation of this particular product, which is the migrated product. This is isomerization of photosantonin to neophotosantonin by a 1,5 hydrogen shift. Please put a double bond over here, which is missing in this particular structure. Now let us move on to a very interesting 3,3 sigmatropic rearrangement, which is known as the Klopp rearrangement or Claisen rearrangement, as the case may be. This is a rearrangement of 1,5 hexadiene into a 1,5 hexadiene. So this is a degenerate rearrangement. Both the starting material and the product are essentially same. In the case of the oxygen substituted allyl vinyl ether, resulting in the formation of a carbonyl unsaturated carbonyl bond, this is not a degenerate rearrangement. This is also not a reversible reaction. This is always proceeds in the forward direction only and not in the reverse direction. These are examples of 3,3 sigmatropic rearrangement. If this is a carbon-carbon bond that is breaking here, or if this is a carbon-oxygen bond that is breaking here, with respect to the bond that is being broken, this is 1, 2, 3, 1, 2, 3. Similarly, this is 1, 2, 3, 1, 2, 3. So this is 3,3 sigmatropic rearrangement of the degenerate type. This is 3,3 sigmatropic rearrangement of non-degenerate type. Please remove this arrow in the reverse direction. It proceeds only in the forward direction. The importance of these reactions are that they are highly stereospecific in nature, so they are extremely useful in carbon-carbon bond forming reaction steps in organic synthesis. That is the beauty of these reactions in organic synthesis. Now the frontier molecular method of analysis of 3,3 sigmatropic rearrangement is shown here. Because these reactions involve a 6-membered cyclic transition state, one can model the 6-membered cyclic transition state as a boat type of a transition state or a chair type of a transition state. The chair type of a transition state is energetically about 2 to 3 kilocalories more favored compared to the boat type of a transition state. So the reaction is often explained by the formation of the chair type of transition state, resulting in the formation of a particular product which can be explained only from the chair-like transition state and not from the boat-like transition state. In both the transition state, of course, it is a superficial migration with respect to all the component. This is the original sigma bond, and you can see here this is the allyl, this is the pi system, this is another pi system. With respect to the sigma, it is superficial. With respect to this pi system, it is superficial. With respect to this pi system also, it is superficial. So it is a 2 sigma superficial, 2 pi antifacial and 2 pi antifacial kind of a migration is what taking place. In other words, it is superficial in all the components that are involved during the course of the migration. Now the 3,3 sigmatropic shift of acyclic 1,5 hexadiene typically takes place around 250 to 300. This is a thermolysis which has to be carried out. The activation barrier is estimated to be about 35 kilocalories per mole. The incorporation of substituent that will bring the olefins in conjugation would favor this reaction. For example, if you consider this reaction and this reaction, in this reaction the reaction will proceed from left to right very nicely, and the reverse reaction is probably not going to take place under this condition, for the simple reason that the phenyl groups are not conjugated in the starting material, but in the product the phenyl groups are conjugated with the olefin. So the extra delocalization energy that one it enjoys in this particular structure will promote this reaction from the left hand side to the right hand side. So if when such a facility exists, the activation energy comes down to about 20 to 30 kilocalories per mole, and the temperature of the reaction is also lowered to about 150. So this particular unsubstituted hexatriene undergoes rearrangement around 300 degrees or so, whereas the substituted diphenyl derivative undergoes rearrangement at a much lower temperature of 150 degree. Of course, one cannot figure out whether this reaction is taking place or not without proper deuterium substituent or something in the position to indicate the rearrangement has taken place. Otherwise, this is a degenerate, non-distinguishable starting material is same as the product kind of a rearrangement is what is depicted in this equation. Now, the mechanism and the stereochemistry of Cope rearrangement is illustrated in these two examples. The dimethyl substituted hexa 1,5-diene can exist in two forms stereochemistry wise. This is the meso form or this is the erythro form. Okay, say either it is a meso form or erythro form, doesn't matter, it implies the same thing. This is a racemic mixture or plus or minus isomer or the trio form of the particular compound that we are dealing with. You can see here the two methyls and the two hydrogens and the two vinyl groups are all cis with respect to each other, whereas here it is not so. So this is the racemic trio form, whereas this is a meso erythro form. What is important here is the stereoselectivity in the Cope rearrangement. If you look at the meso form, which undergoes rearrangement at 225 degrees, it almost exclusively gives the cis trans isomer of the product that is being formed. In other words, the double bonds that are formed here are in a very stereospecific manner. This is a trans double bond and this is a cis double bond. The trans isomer is formed in a very small amount of 0.3% or so. Whereas when the racemic or the trio form is heated to 180 degree, the reaction is faster. First of all, takes place at a lower temperature. It produces almost exclusively the trans isomer. The cis isomer and the cis trans isomer are formed only in a very small amount in this particular instance. How do we explain the formation of stereoselectivity of the product that is being formed? This is by invoking the chair type of a transition state in all these cases. The reaction proceeds through a 6-membered cyclic transition state. Both chair and boat type of transition states are possible. The difference in the activation barrier between the two transition states is about 5.7 kilocalories per mole. This is sufficient enough to show a selectivity in the product formation. The boat type of transition state competes with the chair type of transition state when the reaction is carried out much above 250 degree. In other words, stereoselectivity will be lost if the temperature is very high compared to the temperature at which the reaction actually takes place, namely 220 and 180 degrees respectively for the erythro and trio isomers. Now the trans isomer or the cis trans isomer formation during the course of the rearrangement is explained. The blue structures are essentially chair type of structures for the racemic isomer and the meso isomer, and the red type of transition state, the structures that are shown are the boat type of a transition structure. This is for the racemic isomer and this is for the meso isomer. You can tell, for example, the formation of a carbon-carbon bond here would result in the formation of a carbon-carbon double bond here and a carbon-carbon double bond here. When a carbon-carbon double bond is formed here, this will essentially give the E isomer. Similarly, when the carbon-carbon bond is formed between here and here, that will again form the E isomer. For example, the trans isomer is what is going to be formed. The cis isomer can also be formed from this, but that is going to be a minor process from the racemic mixture from the racemic isomer of this particular compound. Whereas from the meso isomer, when the reaction takes place, it is a cis trans isomer that is going to be formed. This is the newly formed carbon-carbon bond that is taking place, and the newly formed double bond is here and the newly formed double bond is here. With respect to this methyl, it will be a cis double bond. With respect to this methyl, it will be a trans double bond. So the cis trans isomer is going to be the predominant product, for example, formed from a meso-like transition state. Whereas the observation is that the meso isomer gives the cis trans isomer, whereas the racemic isomer gives a trans isomer, which is explained on the basis of the reaction proceeding from the chair type of a transition state. If it were proceeded via the boat type of a transition state, it would have given the opposite stereochemistry for the two diastereoisomers that are reacting, for example. Now, this is a very interesting example of a 3,3 sigmatropic rearrangement. This is cis divinyl cyclopropane. There has been a lot of attempt to prepare the cis divinyl cyclopropane, but it is highly unstable. Even at minus 740 degrees or so, it undergoes a concerted 3,3 sigmatropic rearrangement because of the close proximity of the two double bonds, as well as the release of the ring strain of the three-membered ring, resulting in the formation of hexa 1,4 diene kind of a system that is being formed in the product stage. The cis isomer is much more reactive than the trans isomer, because in the trans isomer the two vinyl groups are further separated from each other because of the trans stereochemistry. So the overlap of this carbon with this carbon is unlikely to take place in a concerted manner. So the reaction does not proceed at minus 40 in the case of trans isomer. It proceeds at a much higher temperature of 190 degrees or so, for example, and this is a non-concerted pathway is what is proposed. It produces a diradical intermediate by the breaking of the carbon-carbon bond of the cyclopropane ring to give diallyl radical derivative. The diallyl radical derivative undergoes ring closure reaction to give the cycloheptadiene as the final product. Although the final product is same, look at the temperature. This is essentially unstable at room temperature, whereas this is very stable at room temperature and reacts only around 190 degrees or so in this particular instance. So the reactivity difference between the cis divinyl cyclopropane and the trans divinyl cyclopropane can be explained on the basis of the close proximity of the two vinyl groups and the further away of the two vinyl groups in the trans isomer during the course of the reaction. This will easily form a cyclic transition state, whereas this cannot form a cyclic transition state. So this is a concerted pathway, whereas this is a non-concerted radical pathway is what is invoked in this particular case. Now you can recall the vinyl cyclopropane undergoing a 1,3 sigmatropic rearrangement. Such a facility is not competing in this particular process. Vinyl cyclopropane, this in fact can proceed through a 1,3 sigmatropic rearrangement. It does not take place because the 3,3 sigmatropic rearrangement has a much more facile and lower energy pathway compared to the 1,3 sigmatropic rearrangement. We have seen the degenerate rearrangement in many cases. The term degenerate rearrangement or the degenerate system is essentially when the starting material is same as the product. So if you look at this particular system, this is divinyl cyclopropyl derivative, except the end of the vinyl group are tied to a carbon in this particular case. So this undergoes the 3,3 sigmatropic rearrangement again to give the same starting material. The two carbons here are with a thick dot is given here indicating the stereochemistry to be cis with respect to the 2 hydrogen. Here again the stereochemistry is cis with respect to the 2 hydrogen. Now in this type of a situation this molecule can exist either in the transoid form or the cisoid form. In other words, the cyclopropyl ring and the two vinyl groups are essentially in the transoid geometry here, whereas the cyclopropyl group and the two vinyl group are cisoid geometry here. The transoid geometry of course cannot undergo the 3,3 sigmatropic rearrangement, whereas the cisoid can undergo the 3,3 sigmatropic rearrangement. So in order to avoid this confusion, if there is an additional bridging between this carbon and this carbon, that would put everything in the cisoid conformation. So such a facility exists in the case of 9-barberalone, which is this molecule here. You can see here this is a cyclopropyl divinyl derivative, except the third carbon of the cyclopropyl is also bridged via a carbonyl functional group to tie up this carbon and this carbon. In other words, these two carbon, namely this particular carbon here and this carbon here, are tied together using a carbonyl functional group. 9-barberalone undergoes a degenerate rearrangement quite readily. Even at minus 60 degrees, this molecule undergoes a very rapid 3,3 sigmatropic rearrangement, which is a degenerate rearrangement. It is not specific only to the 9-barberalone. There are several heteroatom substituted derivatives as well as carbon substituted derivatives do undergo the degenerate rearrangement quite readily, whereas where you have the N-cyano or the carbamate kind of a derivatives here, the sulfur, X is sulfur or sulfur dioxide, they all undergo the 3,3 sigmatropic rearrangement quite readily in this system. Let us come to an interesting example of a degenerate rearrangement of bulvalene. This molecule is called bulvalene. This is the most fascinating molecule or the most fluxional molecule in organic chemistry. So much so that it can generate about 1.2 million degenerate structures by means of a 3,3 sigmatropic rearrangement. Let us see what is the speciality of this molecule. Bulvalene has 3 vinyl groups, and the 3 vinyl groups are attached to a common carbon, which is this particular carbon, and the 3 vinyl groups are also attached in a cis fashion to the cyclopropyl derivative. In other words, this is a cyclopropane which is connected to 3 vinyl groups from all the 3 carbon in a cis manner. The double bond geometry is cis, and the stereochemistry of the connectivity to the cyclopropane is also cis with respect to each other. In other words, this is a C10H10 isomer, and it possesses a C3V axis of symmetry. If we take the center of the cyclopropane and pass it through this particular carbon, that axis would correspond to a C3 axis of rotation for this molecule. With 10 carbons and the C3 axis of rotation, it is possible to generate 10 factorial divided by 3 number of degenerate structure, which corresponds to close to 1.2 million degenerate structure in the case of rearrangement of the 3,3 sigmatropic region. All you have to do is take any one of the carbon-carbon bond of the cyclopropane ring, break it, and connect it via the 2 vinyl groups to the opposite side. So if I break this particular bond, I can connect between these 2 bonds, which would correspond to a 3,3 sigmatropic rearrangement. That would be again bulvalene only in terms of the geometry that is being generated. The molecule has been studied very nicely using NMR spectroscopy, and the NMR spectroscopy, based on the NMR spectroscopy studies, the activation barrier of bulvalene is shown to be about 11.8 kilocalories per mole. This is how the molecule undergoes the 3,3 sigmatropic rearrangement. You can either break AB, BC or AC. If you break AB and connect it over here, then it forms another bulvalene. If you break BC and connect it over here, for example, it again forms bulvalene. If you break AC and connect it over the other 2 vinyl terminal groups here, that forms again bulvalene. So every one of the rearrangement produces a bulvalene. So it is a highly degenerate or the most fluxional molecule that has been known in organic chemistry. This is another way of representing the bulvalene rearrangement through a 3,3 sigmatropic rearrangement. Now, the first example of the asymmetric induction in cope rearrangement is shown in this particular case. Now, before we go there, let me just illustrate the point that the 3,3 sigmatropic rearrangement of bulvalene essentially is studied by NMR spectroscopy. If you look at this particular structure and look at the number of different types of hydrogen, there are 3 cyclopropyl hydrogens attached to the cyclopropane ring. That is one set of hydrogen. Then there are 3 vinyl group hydrogens which are in this particular carbon, 3 vinyl group hydrogens which are in the other particular carbon that is shown here. Finally, there is 1 hydrogen in this. At least there are 4 different types of hydrogen in bulvalene, 1 corresponding to the cyclopropyl hydrogen, 2 types of vinyl hydrogen, and 1 type of the methane hydrogen. When the reaction takes, when the molecule is studied at very low temperature, when the 3,3 sigmatropic rearrangement is extremely slow, one can see all the 4 types of hydrogens in the molecule in separate chemical shift value in the NMR spectroscopy. But when the reaction is very rapid, taking place around 120 degrees or so, because the structure generates other bulvalene, and when the cyclopropyl hydrogens and the vinyl hydrogen and the methane hydrogen become indistinguishable, all the 4 types of hydrogen collapse to a singlet, for example, and that is an illustration of study of the 3,3 sigmatropic degenerate rearrangement using proton NMR spectroscopy of this particular molecule. Similarly, if one studies the carbon-13 NMR spectroscopy of this molecule at various temperature, at very low temperature one would see 1 carbon for the 3 cyclopropyl hydrogen, 1 carbon signal for these vinyl hydrogens, 1 carbon signal for other vinyl hydrogen carbons, finally 1 carbon signal for the methane carbon. When the NMR study is taking place at 120 degree, when the rapid rearrangement takes place, all the 10 carbons become indistinguishable as a result of a singlet is observed in the case of the rearrangement of the bulvalene studied by carbon-13 spectroscopy. This activation barrier has been calculated based on the proton NMR variable temperature proton NMR studies to be about 11.8 kilocalories per mole. Let us come to this example. When the R isomer plus isomer of this molecule is taken and heated, it produces the S plus trans isomer. This is a trans geometry, or R plus cis isomer. In other words, these are the two molecules that are produced from the starting material. This is highly stereospecific in the sense that it produces a S with the trans stereochemistry, or it produces an R with the cis stereochemistry. These are the mixture of compounds that is formed. The S cis and the R trans are not formed. That is why this is highly stereospecific in nature. How is this reaction happening? This molecule can exist in the conformational isomers in the chair form like this. This dotted line is the newly formed sigma bond that is going to be formed during the course of the 3,3 sigmatropic rearrangement. If you look at these two structures, this is axial phenyl and this is equatorial phenyl. So the equatorial phenyl conformer is more preferred compared to the axial phenyl conformer. See the 3,3 sigmatropic rearrangement that is taking place. A new bond is formed between this carbon-carbon bond. This original carbon-carbon sigma bond is broken with the concomitant rearrangement of the pi system to give this. And this again gives the concomitant rearrangement, gives you this particular structure, for example, through a 3,3 sigmatropic rearrangement. While writing these chair forms, you should maintain the R configuration strictly. You should not change the configuration. So you can also see the trans stereochemistry of this double bond is maintained here. This is trans. This is also trans. So once you maintain the R stereochemistry with the trans double bond here, you cannot go wrong in terms of determining the stereochemistry of the final product. These are the two products, and that essentially corresponds to the trans isomer with the S configuration here, and the cis isomer with the R configuration here is what is represented. These two are same as these two structures that are shown here. So what we have seen in this particular module is the sigmatropic rearrangement of 1,5 type, and the suprafacial migration is illustrated by deuterium substitution reaction in the case of the cyclooctatriene case of a molecule which specifically distributes the deuterium in specific places. And then we have seen the 3,3 sigmatropic rearrangement, particularly the cope rearrangement, the stereochemistry of the cope rearrangement involving the cyclic transition state, and then finally the molecule which is the most interesting fluxional molecule in organic chemistry, namely the bulvalene, which undergoes a series of 3,3 sigmatropic rearrangements in this particular module. Thank you very much for your kind attention. I hope you enjoyed this particular module.